Hello friends, welcome back to Operational Amplifier classes. I am Lavanya Vaishnavi. This is the session 4. If you want to refer the previous topics, you can view in my channel. So in this session, I am going to cover two important topics. One is transfer characteristic of op-amp and the other one is linear applications of op-amp. So in linear applications of op-amp, I'll be taking up only 3 topics today. So the rest of the topics we will be covering in the next classes. So which are those? The first one is summing amplifier, that is summer amplifier. The next one is subtractor. The next one is voltage follower. So you have summing amplifier, subtractor and voltage follower. These are the 3 basic applications of op-amp. So these come under linear applications of op-amp. Now the very first one is transfer characteristic of op-amp. To have transfer characteristic of op-amp, let us first assume an op-amp or let me take an op-amp which is connected in open loop. Like you don't have any feedback here. You don't have feedback here. So there is no feedback resistor connected here. Okay. So without feedback resistor, I'll take up a op-amp which is biased with VCC and VEE, which is biased with VCC and VEE. And you give the inputs V1 and V2. V1 and V2. So first, to define this characteristic, before understanding this, let us understand what is the meaning of transfer characteristic. Transfer characteristic is a plot. That is, it is a plot of input voltage versus output voltage. Okay. So it shows, it will represent. So here you can see it represents how your output voltage is varying when you vary the input voltage. When you vary the input voltage, how does the output voltage vary? That is represented in transfer characteristic. Okay, we can see the variation of output with respect to the input in transfer characteristic. So I assume that first I'll make V1 equal to 0. So this value it is equal to 0. So V1 equal to 0 and V2 I am varying it. Like I slightly start increasing it. As you increase the voltage, the output voltage will also increase in the positive direction. Okay. So once your input voltage, that is Vi, reaches the value VCC. VCC is the applied bias voltage to this. Okay. It is the applied bias voltage. When Vi is equal to VCC, you will be having a constant value which is called as saturated value. Your output will reach the saturated value. Now I'll vary the same thing with V2. Now first I'll make a V2 equal to 0 now. Okay, in the first case we made V1 equal to 0. Here I'll make a V2 equal to 0. We will make V2 equal to 0. When V2 is equal to 0, what happens to the output? I'll vary the Vin in, like I'll increase the value of Vin. If I increase the value of Vin, because Vin is given to inverting terminal, the input varies in negative direction. So input is varying in negative direction. Okay. So the output will also vary in the same direction. So the output will start increasing. It will start increasing. Once your input, that is V1, reaches the value of VEE, V1 reaches the value of VEE, then the output gets saturated. Here the output is saturated to minus VEE. So this is the working, or this is the transfer characteristic of op-amp. This is the transfer characteristic of op-amp. So the op-amp transfer characteristic shows that how does the output vary when you vary the inputs. When you vary the inputs. So this is how your transfer characteristic of op-amp look like. Okay, this is how it look like. Clear with us? Okay, let us move on to the next topic. Next is linear applications of op-amp. Now let us see what are all the linear applications are there in op-amp. The first one is voltage follower, summer, amplifier, subtractor, integrator, differentiator, comparator and source converters. In source converters, you have 3 different other techniques, which is voltage to current converter, current to voltage converter, constant voltage sources. So these are the different linear applications of op-amp. Okay. So in this linear applications of op-amp, you need to study the first 6 application: voltage follower, summer amplifier, subtractor, integrator, differentiator, and comparator. Okay, so these topics are not there for your syllabus. So let us concentrate on the first 6 topics. Okay, the first one is voltage follower. As the name suggests, it follows the output. Sorry, it follows the voltage. What voltage it will follow? Voltage follower says that your output voltage follows the input voltage. Your output voltage will follow the input voltage. Okay. So voltage follower says that whatever the output voltage is there, that follows the input voltage. Now look at this point, VA and VB, or node A and node B. We know the concept of virtual ground. This I have discussed in the previous class. Okay. So please understand what is virtual ground. Only then you can understand this concept. So better go with the previous class video and check what is virtual ground. Okay. So now because of taking the concept of virtual ground, I can say that VA is equal to VB. VA is equal to VB. Okay. So if VA equal to VB, what is the voltage at VB? At voltage at VB is Vin, right? Clearly, do you have any resistors here? Nothing. Do you have any other component here? Nothing. Directly Vin is connected to B. Therefore, VB is equal to Vin. The applied voltage is directly given to node B. Yes. Next point, at node A. So now coming to node A, I can clearly say that using the technique of virtual ground, VA is equal to VB. Correct? VA is equal to VB. What is the value of VB? It is equal to Vin. It is equal to Vin. Now I can say VA equal to Vin. Okay? VA value is equal to Vin. If VA is equal to Vin, now what is V0? To understand what is V0, we know that the input impedance of a op-amp is infinity. Right? The input impedance of op-amp is infinity. It means that there is no current flow in this direction. There is no current flow towards the op-amp. That is, whatever the voltage is there at node A, the same voltage you will be having at node V0, right? If this is node X, if I say this is node X, then whatever the voltage you have at node A is same as that of node X. That means even X is at the same potential as that of VA. It means V0 is equal to VA. That is nothing but V0 is equal to Vin. So V0 is equal to Vin. It means the output voltage will follow the input voltage. Output voltage will follow the input voltage. So regarding, I have to specify few important points on it. That is, the gain is unity. The gain is unity. See, look at this expression. You can clearly say that V0 is equal to Vin. It means that what is the multiplication factor here? It is 1, right? So 1 into Vin is Vin, right? So V0 is equal to 1 into Vin. It means that the value of AV is voltage gain is equal to 1. Voltage gain is equal to 1. So if voltage gain is equal to 1, it means that the gain is equal to unity. The gain is equal to unity. It is also called as source follower. What is the meaning of source follower? It says that whatever the source is there, it is following the same thing, right? So if you just look at the input Vin, the same thing you will get at V0. So it is called source follower. And I said you that the gain is 1. Therefore, it is also called as unity gain amplifier. It is also called as unity gain amplifier. It is also called as buffer amplifier. Buffer in the sense that transmit the signal by strengthening it. Okay. So even this voltage follower will strengthen the signal. If it is weakened, it will strengthen the signal and it will transmit. And it is also called as isolation amplifier. It is called as isolation amplifier because it isolates two circuits with its impedance. So we know that the input impedance of op-amp is infinity. Here the impedance will be infinity. Therefore, you will be having isolation between the circuits. Okay. The next slide is regarding advantages of voltage follower. So it is very simple, like it very large input resistance, right? So we know that the input impedance of op-amp is infinity. Therefore, it has large input impedance. Output resistance, we know that the output impedance should be 0. So ideally it should be 0, but practically it has some value, right? So it has very low output resistance. Large bandwidth in the sense it can operate a large variety of frequency. That is, if I take 1 hertz, it can operate. If I take 1 million hertz, it can operate. In between, whatever the frequency you get, like 1 kilo, 10 kilo, 100 kilo, 250 kilo, 500 kilo, like every frequency it will operate. Okay. So the large bandwidth makes it feasible to handle. And no phase shift. No phase shift in a sense, whatever the input is there, like however the input changes, the output will also change. Input and output have the same phase. So if this is your input signal, the same will be your output signal also. Okay. So the same will be the output signal also. There won't be any phase shift. So it won't change like this. Okay. There won't be any changes. Therefore, I can say there is no phase shift. This is one of the important property why voltage follower using op-amp is used in many circuits. Okay. So this is about voltage follower. If they ask you about voltage follower, you have to write the circuit, explain it, like what is the output, and then what are its different names, what is its gain, and finally the advantages. This is a 5 marks question. Okay. Coming back to the summing amplifier. In summing amplifier, we are going to add up 3 inputs. Like here in this example, I am taking V1, V2 and V3. We are taking V1, V2 and V3 as the inputs, and you're going to add V1, V2, V3 to get at the output. Okay. So as the name indicates, it is an amplifier that amplifies the sum of your inputs. Okay. So what is a summing amplifier or summer amplifier? It is an amplifier that amplifies the sum, that strengthens or that amplifies the sum of your inputs. Okay. Which are all the inputs here? V1, V2, V3. Okay. So if you closely look at the circuit, if you just look at the circuit, so if I assume that all these three inputs are one input, then this circuit looks like an inverting amplifier. It looks like an inverting amplifier, right? So we are analyzing this circuit as an inverting amplifier now. V1, V2, V3 are the individual DC inputs. Okay. Now I give V1 through the resistance R1. I give V2 through the resistance R2. Input V3 is given through the resistance R3. The current flowing through R1 is I1. The current flowing through R2 is I2. The current flowing through R3 is I3. All these three current meet at this point X. Okay. And at the point Y, it is divided into two parts, IF and IB. So you have IF here, like it is flowing through RF, and this is IB. Okay. Now we know that input impedance of op-amp is infinity. Input impedance of op-amp is infinity. If the impedance of the op-amp is infinity, IB is equal to 0. IB is equal to 0. So that is what I tell here. The value of IB equal to 0 when input impedance of op-amp is infinity. Okay. So now, because there is no current here, I'll just take up this part. I'll just only take up this part of the circuit. Okay, only this part I'll take. This part. Okay, so if I just take that part, it becomes like this. So it becomes like this. So look at this circuit. You have V1, V2, V3, R1, R2, R3, I1, I2, I3. Similar to that of this circuit, right? And you have this node X, node Y, and IF is the current flowing through RF. And finally reaching at V0. Okay. So this is the complete circuit here. In this, X and Y are at the same potential, right? They are the same points. They are same, right? We don't have any other components here. So X is equal to Y. So look at this. Here in this circuit, this Y is same as this point. This Y is same as this point. Because of virtual ground, this node A and node Y are at the same potential. Node A and node Y are at the same potential. That means Y is virtually grounded. Y is virtually grounded. If Y is virtually grounded, now let me have the current equations here. Okay, so now let me have the current equations here. Now coming to the current equations, in this current equations, first I'll calculate what is I1. To know what is I1, from where to where the I1 is flowing, it is flowing from V1 to Y. It is flowing from V1 to Y. What is the potential at Y? It is 0. It is 0. So I1, I can write it as V1 minus 0 divided by, what is the resistance here? R1. What is the resistance? R1. Similarly, what is I2? It is V2 minus 0 divided by R2. I3 is V3 minus 0 divided by R3. Okay. So look at this. I have taken the same expressions here. I1 is equal to V1 minus 0 divided by R1. I2 is V2 minus 0 divided by R2. I3 is V3 minus 0 divided by R3. Now, what is the expression for IF? To find IF, I can write IF is equal to, from where to where it is moving? It is moving from Y to V0, right? What is the potential at Y? It is 0 minus V0 divided by RF. Divided by RF. Okay. So it is IF is equal to 0 minus V0 divided by RF. Look at this. I have taken IF is equal to 0 minus V0 divided by RF. Now, if I apply KCL at node Y, moving back, look at node Y. Here if I apply KCL, what is Kirchhoff's current law? The current, algebraic sum of current flowing towards the node and away from the node is equal to 0. In other words, I can say the sum of currents flowing towards the node is equal to sum of currents flowing away from the node. So the same thing here I have written, I1 plus I2 plus I3 is equal to IF. If I1 plus I2 plus I3 is equal to IF, I can replace everything by this current expressions, right? So V1 by R1 is equal plus V2 by R2 plus V3 by R3 is equal to minus V0 by RF. See, 0 minus V0 is minus V0, okay? Divided by RF. I need to find the value of V0. So I'll separate V0 and your expression becomes minus of RF divided by R1 into V1 plus RF divided by R2 into V2 plus RF divided by R3 into V3. So in the next step, I'll take all the resistance are equal. Okay, so the same expression I have written here. I'll consider that all the resistors are equal. R1 equal to R2 equal to R3 equal to RF, and let it be equal to R, some constant value R. Then what happens to the expression? The resistance get cancelled here, right? R, everything get cancelled. So you will be remaining with the equation V0 is equal to minus of V1 plus V2 plus V3, which is nothing but the output is equal to sum of all inputs, or I can write output is equal to or output is proportional to sum of all inputs. Hence, it is a summer amplifier. It is a summing amplifier. Okay. So, this is about summer amplifier or summing amplifier. So, if they ask you about this, you have to write the circuit diagram. You have to derive the expression to prove that V0 is equal to minus of V1 plus V2 plus V3. So here you can ask, you got a negative sign here, right? So indicating that the output is inverted. The output is inverted. So even though it is inverted, you are calculating the sum. You are calculating the sum. Therefore, it is a summing amplifier. Hope it is clear. Okay, now move on to the next topic, which is subtractor amplifier. Subtractor amplifier. As the name indicates, it subtracts two inputs. Which are the input that it subtracts is V2 and V1. So the output should be proportional to the difference of input. Output should be proportional to the difference of input. So V2 minus V1 should be the output. So V0 should be proportional to V2 minus V1. So this is our ultimate goal. So that we have to prove it here, or that we have to analyze it here. Okay. Yes. So now coming back to subtractor. So with the same procedure, but I'm going to explain this in 3 different steps. Okay. We have 3 different steps here to calculate. So because you have 2 inputs, till now whatever the inputs you have taken, either this terminal V2 used to be ground or V1 used to be ground. That is, inverting used to be ground or non-inverting used to be ground. But here you have both the inputs are given. Both the inputs are given. So what I have to do is, I'll calculate in 3 different steps. In the step 1, I'll assume that V2 is 0. In the step 1, I'll assume that V2 is 0. So the voltage applied at point 2 is 0. Here V2 is 0. That means that here the applied voltage is 0. If this applied voltage is 0, it means that you are grounding it. You are grounding it. So you can see I have grounded this, right? So it is grounded. Now only V1 is there. You have only V1. If you look at the circuit properly, it is nothing but inverting amplifier, because you are giving V1 to inverting terminal. Therefore, it is inverting amplifier. So if it is inverting amplifier, what is the gain for inverting amplifier? So V01, here whatever the output you get, that is in the step 1. Okay, and you are making V2 equal to 0. It means whatever the output you are taking, that is not because of V1 and V2. It is only because of V1. So this is not your complete output. It is an intermediate output. So I am taking V0 of 1. Okay. So V0 of 1 is equal to minus R2 by R1. So minus R2 by R1 into V1. So where did you get this expression from? This expression is from inverting amplifier. This expression is from inverting amplifier. If you go back to the video or if you refer the notes of inverting amplifier, you will get this expression. You will get this expression. V01 is equal to minus R2 divided by R1 into V1. So in the previous inverting amplifier, you have taken R2 as RF. You have taken R2 as RF. So you can either take RF or R2. Anything is okay. Okay. So this is the expression. In the next part, so in step 2, what I will make is, I will make V1 equal to 0. So if I make V1 equal to 0, that is this part I will make 0 and V2 I will apply. So this I am making it 0 and this I am going to apply. So the same thing I am doing here. I am making V1 equal to 0. Therefore, here it is grounded. And V2 you are applying it. So if you look at this circuit carefully, it looks like a non-inverting amplifier. It looks like a non-inverting amplifier. What is the input you are giving to non-inverting amplifier here? V2. But V2 you are giving through resistance R1. You are giving through resistance R1 and you also have resistance R2 here. Okay, so you have two resistances here. Therefore, which is the potential that you are applying here is this point. So V2 dash is the applied voltage for your op-amp. Therefore, so if you look at the derivation or gain expression or the voltage expression of inverting non-inverting amplifier or non-inverting amplifier, you have, like we have derived it as V naught is equal to V input. So here input is V2 dash into 1 plus RF. Here RF is R2 divided by R1. Okay, this is the expression. Now I have replaced everything here. Okay, so now we don't know what is V2. Sorry, we know what is V2, but we don't know what is V2 dash, right? So to find V2 dash, what is V2 dash? So I will only elaborate this part of the circuit. Only this part I'll take out. Okay, if I just take out that part, you will get a resistors R1 and R2, and V2 dash is the voltage divider point between R1 and R2 using voltage divider equation. If you remember, you have studied about voltage divider equations, right? So that according to that equation, V2 dash is equal to V2 applied voltage across which you are taking the voltage across R2, right? So V2 into R2. So V2 into R2 divided by total resistance R1 plus R2 will give you the value of V2 dash. So if that is the value of V2 dash, you can write the output voltage expression V naught 2, that is V out of 2 is equal to V2 into R2 divided by R1 plus R2 plus 1 into 1 plus R2 by R1. So this is the expression, right? In this expression, if you put this value, like if you substitute here, you will be getting this expression. Okay, so here if you multiply, so if you write this equation here and if you take this LCM here, you will be getting R2 divided by R1 plus R2 into R1 plus R2 divided by R1. So I can cancel this R1 plus R2 and R1 plus R2. You will be left with V naught of 2, that is V out of 2 is equal to V2 into R2 divided by R1. This is the expression. Okay, so this completes second step. Now, third step is I have to add step 1 and step 2, because how did I analyze this subtractor is, so I analyze the subtractor by removing one source, by applying only one source, that I calculate the output, and now I remove the second source, apply the first source, calculate the output. Okay, so this is your first and second step. Third step is I'm adding both the outputs. So now if I add both the outputs, 1 plus 2 is equal to V naught. So V naught is equal to V naught of 1 plus V naught of 2, which is minus R2 by R1 into V1 plus R2 by R1 into V2. Now here I can take common R2 by R1 and R2 by R1. If I take R2 by R1 common, I'll get V naught is equal to V2 minus V1. It is nothing but V naught is proportional to applied voltages V2 minus V1. How it is proportional? To the difference of applied voltages. Therefore, this circuit is called subtractor amplifier. This circuit is called subtractor amplifier. Okay. Hope the steps are clear. So the three steps are, in the first step, we make V2 equal to 0 and we apply only V1, calculate the output. In second step, you'll give a V2, that is you apply V2, you make V1 equal to 0 and calculate the output. In third step, you're going to add up V1 and V2 to get the actual output V0. This is the procedure to calculate V0 in your subtractor amplifier. So we got the equation as V0 is equal to V2 minus V1 into R2 divided by R1. So this R2 divided by R1 is the gain. It is the voltage gain AV. It is a voltage gain AV. So if R2 divided by R1 is voltage gain AV, V0 is equal to AV into V2 minus V1. If AV equal to 1, that is, if I think or if I assume that both R1 and R2 are equal, AV becomes 1. So that means V0 will be equal to V2 minus V1, which is V0 is proportional to the difference of input. V0 is proportional to the difference of input. Okay. So that's all for the day. Thank you for watching this video. Please like the video, share the video with your friends and subscribe to my channel. If you have any doubts, you can write me back to my email ID. Thank you.